Today we're going to be focusing on the meaning of calculus expressions in the context when we're given a worded situation. All right. So it's very common question on the AP exam, and with good reason, because we should know the meaning of these expressions. We should know the meaning when we're taking a derivative, when we're evaluating an integral. We should know what our answer means, right? So it makes sense. I'm going to break this down into 3 different integrals that cover most of what you'll be asked to do. Okay, let's say that we're in a worded situation, we're given some function, and let's just say that that function is w. I tried to pick some different, I didn't want to call it f, because when we get stuck with f, it tends to lose its meaning. So W, it means something. Maybe it's the water temperature. Maybe it's the amount of water in a tank. Maybe it is, maybe it's the height of a tree. Maybe it's, whatever. But this is our function. And the independent variable, let's call P. Most of the time, that'll be time, T for time, but not always. So I'm going to call it P just in case you come across some different problem where it's not time. Okay? So we will most likely be given a table of values, W values for selected values of P. And when we're given something like this, you could be asked to approximate an integral with a Riemann sum. You could be asked to approximate a derivative at a specific p-value. There are lots and lots of things that they could ask you when they give you a table of values. One of the things that's common is for them to ask you what it means. What does that derivative mean? What does that integral mean? So approximate that derivative and then give the meaning of it. So in this problem, you would probably be first asked to use the table, the values in the table, to approximate W prime at 75 or some p-value, using correct units in the context of the problem. Okay, so what I'm going to provide here is a template that you can use. This is by no means the only way you could answer this question, but if you follow this template, you will always be expressing everything that you need to express. So it begins with at the 75, so we're given the meaning of the 75. What does that 75 mean? Well, if P was in seconds, it would be at 75 seconds. If P was in millimeters, it would be saying at 75 millimeters. So don't forget your units of P there, okay? And then a derivative is a rate of change. Every derivative is the rate of change of something. This is the rate of change of W. It's the rate of change of W. So I can say that W is changing at a rate of W prime at 75. I want to say W, but we need to give the meaning of W. Is it the height of the tree? Is it the temperature of the water? Is it the amount of oil? Whatever it is, we need to say the meaning of W is changing at a rate of W prime of 75, and then you always follow with units of your answer, units of W prime. So, what are those units of W prime? Well, W prime, another way to write W prime is dW dP. So the units will be units of W divided by units of P. So units of W divided by units of P. Every time, W prime. Units of W, units of P. Alrighty? Okay. A word of caution. Be careful if you use, instead of saying changing at a rate of, sometimes it's more comfortable to use the word increasing or decreasing at a rate of. Be careful with that, because if you use decreasing, if you say it's decreasing at a rate of W prime, and if W prime is negative, then you're no longer decreasing, right? Decreasing at a negative rate means it's increasing. Okay, so just be careful if you do that. You could say it's increasing at a negative rate, but even that is a little bit misleading, okay? So my best advice is to say changing at a rate of. One more thing before we leave this. Oftentimes, like I said, oftentimes in these problems, you've just now approximated this. Using the values in the table, you've approximated this derivative. Do not use your approximation there. They are asking you to explain the meaning of W prime, not your approximation. So use W prime here, okay? Not your approximation. Okay, next step, integrals. So there are two integral expressions that you will likely be asked to give the meaning of. Let's say that they ask us for the integral from 0 to 100 of W prime, or 1 over 100, the integral 0 to 100 of just W, no prime, just W. Let's focus on this one first. This is, we need to recognize that. That is the formula for the average value of a function. 1 over b minus a, integral a to b of the function. That gives us the average value of f. So this is the average value of w. That is the average value of w. There's no prime there. It's just the average value of w. Okay? Think of the units of this thing. Think of its units. I'm going to write WP, W of P, dP. What would be the units? Well, what would be the units on W of P? Well, whatever those are. So we'll say, call them W units, okay? What would be the units of dP? Well, we'll call those P units, yeah? What would be the units of 1 over 100? Well, the 0 and 100 are P values. So 1 over P values. This would be 1 over P values. So we will get back, when you multiply these together, we get back W units. Units of W. Okay? Let's do the same thing on this expression. Okay. We have the integral. Units of W prime. What are units of W prime? Well, W prime has units of W. We just talked about this. Units of W over units of P. dP has units of P. And you're left with units of W. This will give us units of W. They both give us units of W. Okay? They both give us units of W. Okay? This is, when you take the integral of W prime, you get back W. But with boundaries, this is change in W. Not change in the rate of W. Just change in W. This would be W of 100 minus W of 0. Fundamental theorem of calculus. Change in W. Okay? So for the meaning of that first one, from 0 to 100, from 0 to 100, and then whatever your P units are, the change in W, only we don't write W, we write the meaning of W. The change in the height of the tree. The change in the temperature of the water. The change in the amount of oil in the tank. Whatever it is, the change in W is this integral and then units on it, since it's change in W, units of W, whatever those are. Always 2 sets of units for these. 1 unit of the meaning of the 0 and 100, and then 1 unit for, or 1 set of units for your answer. Okay? So this is the average value of W. So from 0 to 100, units of P. The average W, the average height of the tree, the average temperature of the water, the average amount of oil in the tank, whatever it is, the average, not rate of change, just the average, okay, is this integral expression, and then once again, units of W. Always 2 sets of units. Okay, let's take a look at some examples. Alrighty, the height of a tree at time t is given by a twice differentiable function h. H of t is measured in meters, t is measured in years. Selected values of h are given in the table. Using correct units, explain the meaning of h prime of 6. So in an actual problem, they probably would first have you approximate h prime of 6, for which we would use the 2 closest points. H prime of 6, we would find the average slope between those 2 points. What is the meaning of it? Well, at 6 years. At 6 years. H is changing at a rate of. H is changing at a rate of, but I don't put H, I put the meaning of H. What is the meaning of H? H is the height of a tree. So the height of the tree is changing at a rate of that derivative, not your approximation, that derivative. And now we need units on h prime, which are units of h over units of t. So meters per year. Okay? Part B, using correct units, explain the meaning of this integral. Okay? The integral of h prime gives you back h. So this is change in h. So from 2 to 10 years. From 2 to 10 years, the change in h, the change in h, but we don't put h, we put the meaning of h. The change in the height of the tree. Is this integral expression, and then the units of h, only h, because you're going to get back h, so units of h only, meters. Part C, using correct units, what's the meaning of this? Well, I recognize as soon as I see this coefficient right here, the coefficient is your cue to use average value of a function. So this is going to be the average value of a function. Average value of h. Okay? So I'm first going to begin with the meaning of the 2 and 10. So from 2 to 10 years. The average, not the average rate of change, just the average h. But we don't say h, we say the meaning of h. The average height of the tree is this integral expression, and then the average height of the tree will have tree height units, so meters. Okay? I want you to notice that in both of these integrals we get back h units. We get back h units. The only one that changes is the derivative. It's meters per year. Okay? Alrighty. Here we have another one. The density of a bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f, where f of r is measured in milligrams per square centimeter. So we have a petri dish, a circular petri dish, and there's a bacteria sample on it. And it says that at a distance r centimeters from the center of the dish. So our independent variable is not time, it is r. And r means the centimeters from the center of the dish. Okay? And it's given by an increasing function. So the density is increasing as we get further and further from the center. So inside, close to the center, we only have a few bacterias. Okay? But as we get further away, it's thicker, there's more. Okay? And the further we get away, the more there are. The density is increasing as you get further from the center. Okay? So it's sometimes helpful to get an idea of what's going on. Alright, selected values of f are given in the table. Using correct units again, explain the meaning of f prime of 2.25 in the context of the problem. So prime is a rate of change. This is rate of change of f. Rate of change of f. So at 2.25, we need unit. What is the meaning of that 2.25? 2.25 is the distance from the center of the dish, true? And its units are centimeters. Centimeters. Is that enough? Is that sufficient? At 2.25 centimeters. Would that be enough to say at 2.25 centimeters the density is changing at a rate of whatever? I would elaborate on the meaning of 2.25. At 2.25 centimeters from the center of the dish. At 2.25 centimeters from the center of the dish. F is changing at a rate of, but I don't say F, I say the meaning of F. And the meaning of F is the density of a bacteria population. So the density of a bacteria population, or the bacteria population, is changing at a rate of f prime at 2.25, and now units of f prime. F is milligrams per square centimeter. So f prime is milligrams per square centimeter per centimeter. So that's what I'm going to write. Milligrams per square centimeter per centimeter. Another way that you could write that is milligrams per centimeter cubed. You could say that, okay? But we had a discussion on this in a couple of the classes, and that confused some students. Some students thought that centimeters would cancel out or something, and they were saying that it would be milligrams per centimeter. And that is wrong. It's not milligrams per centimeter. It is milligrams per cubic centimeters. Or just write it out in words like this, and you'll never go wrong. All right, using correct units, explain the meaning of this now. Okay, this is the integral of the integral of f prime. We know it gives us back f. So this is change in f. So from 0 to 4, and what's the meaning of that 0 to 4? Centimeters from the center of the dish. The change in f, but we don't say f, we give the meaning of f. The change in the density of the population, of the bacteria population, is. Not is changing at a rate of, it's just is. The change in density of bacteria is this integral expression, and now units on that. This is just units of f, whatever f's units are. So milligrams per square centimeter. Okay. Last one here. Using correct units, explain the meaning of this one. So we recognize this is a recognized thing, as the average value. That 1/4 out front, that coefficient out front gives it away. This is the average value of f. Okay? So from 0 to 4 centimeters from the center of the dish, the average f, the average, but we don't say f, we say the meaning of f. So the average density of the bacteria population is that integral expression. It is not an average rate of change, it is just the average f, okay? So we get back f units, milligrams per square centimeter. Okay? Let's do another one. An ice sculpture melts in such a way that it can be modeled as a cone. So we have this conical ice sculpture that is melting. And as it melts, it maintains its conical shape. Okay? The radius of the base of the cone is given by a twice differentiable function r. So r is the radius of the base. So as it melts, r is getting smaller, where r of t is measured in centimeters and t is measured in days. The table gives selected values not of r. The table gives selected values of r prime, not r. R prime is the rate of change of the radius. Okay? So this is a little bit different because we don't have r in the table, we have r prime in the table. So in part A, they're not going to ask us what the meaning of r prime is because they've already told you what r prime is. They're asking you, what is r double prime then? Well, r double prime is the rate of change of the rate of change. Yeah? It's the rate of change of r prime. So it's the rate of change of the rate of change of the radius. But that's going to sound awkward. So let's use my template. Okay? So we begin with at. Not until, not through, not before, not during, at exactly 5 days. At exactly 5 days. R prime is changing at a rate of this. R prime is changing at the rate of that. So I need to give the meaning of R prime, and R prime is the rate of change of the radius. So the rate of change of the radius is changing at a rate of R double prime of 5 units of R prime over units of T. So centimeters per day per day. Or you could say centimeters per day squared. Okay, either one. Using correct units now, let's explain the meaning of the integral of R double prime. Well, the integral of R double prime is going to give us back R prime. Yeah, the antiderivative of R double prime is R prime. We go back a degree, we go back a derivative, yeah? So, this is change in R prime. Change in R prime from 0 to 12 days. The change in R prime, but I don't say R prime, I say the meaning of R prime. The rate of change of the radius. Is that integral expression. Integral 0 to 12, R double prime of T dt, and then units of R prime, centimeters per day. Okay. Using correct units, explain the meaning of this one. Okay. Well, we recognize that it is the average value. And what is it the average value of? Whatever function is sitting in your integral. Whatever the integrand is, it is the average value of your integrand. So it's the average value of R prime from 0 to 12 days. The average R prime, the average rate of change of the radius. Is this integral expression and then units of R prime, centimeters per day, units of R prime. Okay, one more. We did not do this one in class. I had everybody save it to do on their own and then check your answers using my notes in the Google Drive folder. Okay, so if you want to turn it off now and do that, that's fine. But I'm going to go ahead for the sake of notes and go ahead and do this one too. So a customer at a gas station is pumping gas into a gas tank. The rate of flow of gasoline is modeled by a differential function f. F is in the table, and f is the rate of flow of gasoline. That's what F is. So F is a rate, gallons per second. F is already a rate. Time T is in seconds, so the independent variable here is seconds. Okay, so T is measured in seconds since pumping began. Selected values of F are given in the table. Using correct units, explain the meaning of F prime. Well, it is the rate of change of F. The rate of change of F. F is already a rate, so it'll be a rate of change of the rate of flow of gasoline. at 105 seconds. F is changing at a rate of this. So F, only I don't say F, I say what F means. The rate of flow of gasoline. Is changing at a rate of F prime of 105. Now units of F prime. F is gallons per second, so F prime will be gallons per second per second. Gallons per second per second, or gallons per second squared. Okay? Now let's explain the meaning of this integral. So it's the integral of F prime, so I know I'm going to get back F, therefore this is change in F. Change in F. So from 0 to 150 seconds. From 0 to 150 seconds. The change in F. The change in F. Not the rate, the change in F. But I don't say F, I say what F means. The change in the rate of flow of gasoline. Is this integral expression units of F. Units of F, so gallons per second. Okay, one more here. Using correct units, explain the meaning of this integral expression. We recognize it as the average value of F. Average value of F. So from 0 to 150 seconds, the average, not the average rate of change, I see that a lot, just the average F. F is the rate of flow of gasoline. So the average rate of flow of gasoline is this integral expression units of F, gallons per second. Okay, so I am hopeful that this helped break it down a little bit, give you a little practice just with giving meanings of these. I'm hoping it made sense. There's always one of these, as there should be. We should be able to know what these things are. So it makes sense. Okie doke.